Hey there. I want to go over the test and talk about the solutions to each of the problems. I'll be honest, the test scores were not where I want them to be. There were some very good scores, but there were also some very bad scores, and I think needlessly so. So let's talk about these problems, and then at the end I'm going to tell you how you can get some of those points back. And I apologize ahead for the shirt. I realize I got this crazy moire thing going on with my striped shirt. I didn't think about that when I put it on, but you'll just have to endure that. Let's go through and work these problems, starting with problem 1, which asks us to prove that the sum of an odd number and an even number is an odd number. It's pretty straightforward. This is a direct proof. We need a couple numbers. We need an odd one, and we need an even one, and then we just need to add them, right? So let's go through and do that. I don't know why these notification things are going on. Is that going to call up the... I was afraid of that. I don't want to know. I don't want to know. Stop. Connect lesson. Okay. Sorry about that. Let's go back and do this. So let's let, I don't know, A be an odd number. And what does that mean? Well, it means that there's some integer, I don't know, m out there such that A is 2m plus 1. Okay? And now we need an even number, so let's let B be an even number. And that means then that there exists n that's an integer such that B equals 2n. That's what we mean by an even number. One of the big mistakes I saw on the test was picking the same integer for both A and for B, or for whatever you call them. The problem with that is that makes them consecutive integers, and we can't have that. We've got to do this in general. So now that we've got our two things and we've got them defined as necessary, let's consider their sum, A plus B. So A plus B would be, A is 2m plus 1, and B is, sorry, that's kind of messy. B is 2n. So got my things with 2's in them. I'm going to put them together. 2m plus 2n plus 1, and I'm going to factor that 2 out. Okay. Well, m plus n is an integer, so we say something to the effect, since m plus n is an integer, then A plus B is an odd number. And there you go. That's it. That's all there was to that. We had worked several problems kind of like that, and I think even when we did it, I cautioned you about the don't use the same integer for both, because to be completely general, they have to be different. Okay. So that's problem 1. Let's look at problem 2. Problem 2 says, okay, if x cubed is irrational, then prove that x is irrational. Now, we talked about this type of thing as well. We do not have a good way to represent irrational numbers because irrational numbers are basically not rational. So we do have a good way to represent rational numbers, but we can't just say they're not like this. That doesn't help us if we're trying to do things with equations and so forth. There's one or two routes you can take with this. You can assume that x cubed is irrational and then assume the opposite, assume x is rational, and then show that that forces x cubed to be rational. That's one way to go about it. This is perhaps a more straightforward contrapositive proof. So I will say that let's consider the contrapositive. Which says this: if x is not irrational, which is rational, then x cubed is not irrational, which is rational. Okay? And then we can prove that with direct proof. It's actually not too hard. We did several like this. Let x be a rational real number. And what does that mean? Well, it means then there exists I don't know, P and Q? P and Q that are integers. Q actually has to be non-zero, such that x is equal to P over Q. And that means that x cubed is P over Q cubed, which is P cubed over Q cubed. And P cubed is going to be an integer still. Q cubed is going to be an integer still. Q cubed will still be non-zero. So we say all that. Since these are integers and Q cubed is non-zero, then that tells us that x cubed is a rational real number. The only other thing left to do is just kind of say, okay, since the contrapositive statement is true, then the original statement is true. And the original and that's it, you're done. So again, once we consider contrapositive, very direct proof, it's very similar to a lot of the rational number proofs that we did in our homework. All right, so that's 2. Let's call up problem 3. Problem 3 says, okay, if and we're dealing with integers here, integer n, that the following statements are equivalent. That 3n plus 2 is even, that n plus 5 is odd, and that n squared is even. And a lot of you were able to kind of deduce that this comes down to the fact, in many cases, that n is going to have to be an even number. But that's not enough. What we've got to do is say, okay, well, one of these implies the other, which implies the other, and then bring it back around to the first one. It doesn't matter what order we do things in at all, as long as we get them all connected. But if you start out and say, well, okay, then look, this is even, and since n is even, this happens, this happens, this happens. Well, that's fine. Even gives you this and this and this, but that doesn't connect them. Okay, what you'd have to do then is go back and say, well, this means this is even, this forces this to be even, this forces this to be even. So they're all connected in that way. What you've basically done is thrown in a fourth statement, which just, in a way, kind of makes it a little more complicated. I think what I'm going to do is just take it straightforward, let A prove B, let B prove C, then let C prove A. So let's go through and do that. A proving B looks like this. We will let 3n plus 2 be even, which is fine. And this is a point where we would typically say, okay, then there exists a k or something out there such that this is 2k. However, that's not going to be enough, because when we solve for n, we're going to be dividing by 3, and we're going to have 2n divided by 3. That's not obvious what's happening there. But that does force, if you think about it, that does force n to be an even number. So let's show that. Let's assume for a moment that it's odd. Okay? So suppose, and anytime I'm doing contradiction, I like to use the word suppose, because we're not actually going to, this is kind of pretend land we're jumping into here. Suppose n is odd. And so that means, again, that there exists a k. It's an integer such that n is 2k plus 1. Okay? Now, the way I'm going to show this is bogus is I'm going to go back and show then that 3n plus 2 must then be odd, which is a contradiction. We've already said let 3n plus 2 be even. That is a given. So then (3n plus 2) would be 3 times this 2k plus 1 plus 2, which is 6k plus 3 plus 2, which I'm going to pull one of those 2's back in there. Oops. Which would be 2 times, and I'd have 3k plus 2, that's 4, and then I'm left with 1. So since 3k plus 2 is an integer, then 3n plus 2 is odd, and that is a contradiction. Thus, n is even. And now we're on to a different proof. So if I want to use k again, I can't. You know, I'm done with k from the first use. And there exists I can use something else if I want to, but I can certainly use k again. 2k. Then now I'm ready to look at n plus 5, right? And I'm going to pull 4 out of that 5. And since k plus 2 is an integer, that means that n plus 5 is odd. And we've got the first one done. That is A proven B. Now let's do B given us C. So again, let this be odd. And this is one, since we want to solve for n, we don't have to divide by anything. It would be a good time just to jump in and say, okay, then there's some k. We can use k because we're on to a different proof now. Then there exists k, integer, such that n plus 5 is 2k plus 1. And that means that n is equal to 2k minus 4. Now I bet you know where I'm going next. We're going to now look at n squared, right? Since I'm going to prove C, I want to look at n squared. Then n squared equals 2k minus 4 quantity squared, which is 4k squared, minus 16k plus 16, but of course I can pull a 2 out of all of that, right? 2k squared minus 8k plus 8. And now this is the part where we say, well, since that business in parentheses, 2k squared minus 8k plus 8 is an integer, then n squared is even, and we're done. Okay, so we're 2/3 of the way there. That is our if B then C proof. And now let's look at if C then A proof. So we start with C, let n squared be even. Now again, this is a point where a lot of times we would jump in and say, okay, you know, that therefore there exists a k out there such that n squared equals 2k. Now here's the problem. We want to deal with n and not the square root of all that, right? So what we probably have to go with instead is showing that, well, that means that n itself has to be even, okay, which will be sufficient to get us to 3n plus 2 being even. So again, I would say, suppose n is odd. This is very much like the proof we did in the first part. Then, and you know this routine, there exists k, we keep using k because we're on to a different proof now, such that n is 2k plus 1. Then let's look at n squared. What I want to do is get a contradiction and show that n can't be odd, it must be even. Okay, so n squared in that case is 2k plus 1 quantity squared, which is 4k squared plus 4k plus 1, and I can Factor 2 out of those first bits, right? 2 times 2k squared plus 2k. But I got this 1 left over. Since that business in parentheses is an integer, then n squared is odd, which is a contradiction to our assumption. Thus n is not odd, it is even. And there exists, now we're on to a different proof, so I can still use k if I want to. Such that n is 2k. And so now we're ready to look at 3n plus 2. This is 3 times 2k plus 2, but you can see that I can factor a 2 out of all of that, right? I'm left with 3k plus 1. And since 3k plus 1 is an integer, by the way, that's a very important part of this odd and even business. If 3k plus 1 is an integer, that tells us nothing about 3n plus 2. You know, pi, I can write pi as 2 times something. Pi is 2 times pi over 2. It doesn't make it even. Doesn't even make it rational, right? So since this is an integer, then 3n plus 2 is even. And that has got then C equivalent to A. So you got this nice little circle, nice little triangle, I guess, really. 3 points, right? The last thing to do is to just kind of sum it up with a therefore. The statements are equivalent. Boom, and you're done. Okay? So that's problem 3. You could do it other way. I mean, you start with any one of them and kind of go around. If you are going to throw in that even thing, though, you got to take it back. You can't just say even gives me this. You got to say this gives me even as well. All right, so let's go to the 4th problem. These 4 and 5 are set proofs, so we are doing some of the trickery we did with sets. So we want to prove that this thing equals this thing. The best way to do that is the double set inclusion. Let x be a general element of the left-hand side, show that it belongs on the right-hand side. Then let x be a general element of the right-hand side, prove that that belongs on the left-hand side. That means this is a subset of this is a subset of this, and we're done. So I will start with the left-hand side. Let x be an element of A union B minus C. Now what that means is that then x is in A union B, but x is not an element of C. And since it's in A union B, that means then x is in A or x is in B. And that's what we have to look at here are the cases that pop up. So if it's in A, and remember our target up here, this is what we're trying to see. If it's in A, but it's not in C, then it is in A minus C. And that means it would be in the union of A minus C and any other darn thing on earth. but in particular B minus C. Okay. If it's in B, but we have up here that it's not in C, then X would be in B minus C, and that means X would be in B minus C union with any other thing on Earth, but in particular A minus C Thus, what this is telling us then is that that left-hand side is a subset of the right-hand side. Okay? So that's half of it. Now let's let X be an element of A minus C union with B minus C. Now what that means is X is X is in A minus C, or possibly X is in B minus C. Okay? So we have to look at those two cases. If X is in A minus C, stop, out, sorry. If X is in A minus C, then that means it's in A, but it is not in C. If it's in A, it would be in A union anything, and particularly A union B. And since it's not in C, that's an and. Let me do better. So that's the target on the first one. Now let's look at the second case. If X is in B minus C, then X is in B, but not in C. But if it's in B union with anything, in particular A. And that means that it's in A union B. We know it's not in C. So either case, that means that this A minus C union with B minus C is a subset of A union B minus C. Now, since this is a subset of this, and this is a subset of this, that means they're equal. So the last statement is, therefore, A union B minus C is equal to A minus C union with B minus C. And we're done. Okay? And that's the fourth one. Okay, and then let's take a look at problem 5. Okay, now this is one where we've got a set that we're going to show that's empty to the empty set. So these are pretty much always proofs by contradictions, right? You say, well, let it be in this thing that's equal to the empty set, but the empty set has no elements. So as soon as you say that, it's a suppose, and then you're going to say, and then you're going to prove that it just can't exist. Okay? So we start this one by saying something like, suppose x is an element of this crazy thing on the left, this a minus b intersecting b minus a. And what does that mean? Well, it means then x is an element of both a minus b and this is important, and or are important connectors there. Many of you on the test were just putting commas. And it really kind of matters what you say here, because if it's in one or the other, you have to look at the cases. If it's in both, you have to assume it's in both. So and or are very important in these proofs. So it's also in b minus a. Now, what does that tell us? Well, it tells us then that x is in a, but x is not in b. It also tells us that x is in b. But that's a contradiction. I mean, it goes on to tell us that x is not in a, which is another contradiction, but in particular we just need one. Thus, and this is where we need a little English, there are no elements in a minus b intersect b minus a, and that means then that equals the empty set. And that's it. That's all we had to do. Alright, let's see. Get down here to the sixth problem. 6 and 7 were our straightforward mathematical induction proofs. With this particular one, we want to prove this for all an integer n greater than or equal to 1, which means basically natural numbers. I prefer integers, 1 and bigger, but your book a lot of times will say natural numbers, so it's fine, that's fine. So we start with the basic step here. The initial step is we say, well, let's show that it holds for n equals 1. So I'll say something to the effect, note that, and we look at the formula here on the left and just take it up to 1. So this is 1 times 2 to the 1, which is 2. And then we look at the formula here and plug in a 1. 1 minus 1 times 2 to the 1 plus 1 plus 2. Well, this is 0. Plus 2 is 2. Since those are equal, we say thus the initial step holds. Okay, so that's the first part. Now we do the inductive step, and we say, all right, let's let this hold for a certain k out there. It's got to be 1 or bigger. So I going from 1 to k, I times 2i. We'll let this be k minus 1, 2 to the k plus 1, plus 2. For some, and you can say integer here, but it's an index, it has to be an integer. For some integer k 1 or bigger. And now what we want to consider is the next sum, if we bump that up to k plus 1, we want to look at this. Okay? Now, keep in mind what we're shooting for here, and this is something that I always put on scratch paper somewhere else. Let me put it in a different color so that you don't get too bent out of shape here. But what we're looking for is when we plug in k plus 1 into that formula, we're going to get k plus 1 minus 1. So that is k. And then we'll have 2 to the k plus 1 plus 1. So that's k plus 2. And then plus 2. So that is what we're shooting for. Keep that in mind. But you can't automatically say they're equal. And I had folks do this on the test. You've got to prove that. And you prove it by going back and using this. Okay? So keep that in mind. That's scratch paper work. Let's go back over here and take a look at I goes from 1 to k plus 1, I 2 to the I. This is going to be the sum up to k, which I know something about, right? I have an assumption regarding that. And then the k plus 1 term here would be k plus 1, 2 to the k plus 1. Okay, that's just what happens, right? Sorry, I'm pointing with this. That's just what happens if you plug a k plus 1 into this. K plus 1 here, k plus 1 there. Okay? All right, so our assumption tells us then that this part right here is k minus 1, 2 to the k plus 1, quantity, plus 2. And then we have added this other term, the k plus 1, 2 to the k plus 1. Well, you've got a 2 to the k plus 1 there as a common factor. So pull that out, and you're left with k minus 1 plus k plus 1. And then you got your plus 2 outside the parentheses there. Well, the minus 1 plus 1 cancel each other out. You do end up with 2k times this 2 to the k plus 1. And you got your plus 2. So the plus 2 is right on track, right? If you look at this, keep this in mind, the plus 2 needs to stay alone there. It's good. That additional 2, I've got 2 to a power, so I can pull that in. That's another 2 to the 1 being multiplied there. So this is k I can leave alone, and I've got 2 now to the k plus 2 quantity plus 2. And that's what I was trying to show. Right? That matches up with what we've got here. Thus, the inductive step holds, and so now you just need to bring it all home. Therefore, by induction, you don't have to rewrite it, but just say the formula. That's kind of sloppy. Let me do better. Holds for integer n greater than or equal to 1. And you're done. That's it. Okay. Had a gamut of things. Probably the most offensive thing I saw with people assuming that this was true. And then also people just plugging in the k plus 1 and using the formula and saying, there you go, that's what you will see. Well, obviously you plug k plus 1 into this, it's going to get you the right answer. That's what you do to get the target, right? But you've got to start with what you have and get a chain of equalities. Oh, the other thing I saw which was highly offensive is setting it up as an equation, which you cannot do. You cannot assume that it's true until you have proven it. but setting it up as equation and then moving stuff from one side to the other. You absolutely cannot do that. That is, we talked about the first day, there's a difference between a chain of equations, chain of things that are equal or inequalities, a chain of these things, and an equation, right? A chain of expressions, let me say it right, a chain of expressions that are equal or greater than, whatever, less than, whatever, and an equation. An equation, yeah, we got rules, we can do things to both sides. We don't have sides in this. We have this, which is equal to 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 this, and finally you get it where you want it. Okay? But you cannot set that up as an equation. We're trying to prove that those two things are equal, not solve for something in the equations. Okay? We cannot, absolutely cannot do that. So let's take a look at problem 7. I think this is 7. There we go. Now this one's perhaps a little tougher because it's an inequality, but it's really not too bad. In fact, it works out quite nice. So we want to prove this for integers 2 or bigger, and so we have to start with 2. So let's note that, and we go to this formula and let n be 2. So we've got the first term, 1 over 1 square, plus 1 over 2 squares, the second one. When you add that up, it's 1 plus a fourth, so that is 5/4. And then when we look at the right-hand side of that inequality, that would be 2 minus 1/2, which is 3/2, but 3/2 is bigger than 5/4, right? Since 3/2 is bigger than, maybe I should state it the way it's stated here. Since 5/4 is less than 3/2, the initial step holds. Okay? All right. Now, assume that the inequality holds for some k. So I going from 1 to k of 1 over I squared is going to be less than 2 minus 1 over k for some, and we'll say integer, but it's implied because it's an index. Okay, and it's got to be 2 or bigger because that's where we're starting. Okay, and we want to consider what happens if we bump that up to an additional term. So I went from 1 to k plus 1, this 1 over I squared, and that's it. Now, our target, let me again do this in green, okay? Our target is we want to be able to say that this is less than or equal to 2 minus 1 over k plus 1. But you can't say that right out of the gate. And I had a lot of folks do this. That is what you have to show. Again, this is not going to be an inequality, okay, that we solve for something. This is going to be this, which is equal to or less than or whatever, this, and then this, and then this, and then this, and this, until you get to that. Okay, you cannot assume that right out of the gate, and I've harped on that and harped on that, but still I saw that on the test, and I'm a little disappointed with that. We go back and we look at this sum, k plus 1, 1 over I squared. Okay, now we're going to use this fact right here. This is our assumption. We're going to use that assumption. This is I going from 1 to k of 1 over I squared plus one more term, and that's the k plus 1 term, which is 1 over k plus 1 squared. Okay? So immediately, let's use the fact that we know here about the first k terms, I know that that part is less than, strictly less than 1 over, 2 minus 1 over k. I still have this 1 over k plus 1 squared term out here. It makes sense, we want to, if you look over here, we want to leave this 2 alone. I think the 2 is fine right where it is, but we want to make sure that the thing I'm subtracting looks like 1 over k plus 1. It makes sense to me to get a common denominator between those two fractions. So the next step here would actually be equal to the previous one. Okay, the whole thing is going to be less than because of this less than right here. But this part is going to be equal to the next thing I write, which is 2. And it's easier for me to do this as a plus. That way I can keep track of the minuses up in the numerator here for just a moment. So my common denominator is going to be this. Let me do this one first. So this would be k, and then minus k plus 1 quantity squared. Okay? Which again, I'm still doing equals here. 2 plus, so let me do a little bit of arithmetic here. This would be k, and then it's k squared, so it's a minus k squared. It's 2k, so it's a minus 2k. And it's plus 1 when you square that, so it's a minus 1. This is all over k plus 1 squared. So it turns out now that each term up there, the k minus 2k is going to be a minus k. Every term there has a negative, so I'll pull that negative out now and write this as k squared plus k plus 1 over k plus 1 squared. Now, this is where it helps to look at what you've got. Right, I want k plus 1 in the bottom, and I've got an extra factor of k and an extra factor of k plus 1. Well, do you notice that if this 1 were gone, that would take care of those 2 extra factors? I'd be left with k and k plus 1 at the top. And certainly I can do that. If I subtract something a little less away from 2, I get something that's a little bigger, right? So this is where I pop in and say, okay, that's fine. This is the slightly less than k squared plus k over k times k plus 1 squared. And that, my folks, my friends, my students, is actually equal to 2 over 1, 2 minus 1 over k plus 1. The k term factors out, the k plus 1 term that I had extra factors out, and I'm left with that. And that's what I wanted to show. Thus, the inductive step holds. Therefore, by induction, the inequality holds. And I could stop there, say for integer n 2 or bigger. Okay, and that's problem 7. It really wasn't that bad, and I think people made it to be, that was one that roughed a lot of people up, needlessly, I would think. You know, the problem with the inequalities, I'm sure, is that you have some freedom there, but it was a glaring thing to do. You know, taking that 1 out of there was just a glaringly obvious thing to do, and that's why I chose the problem. All right. And then the last one is number 8. Let me make sure I've got 1, 2, 3, 4, 5, 6, 7. There we go. This is a strong induction proof, but it's really a fairly sweet and easy one, right? We want to use strong induction to prove that all whole cent postage amounts, 18 cents and above, can be formed using just 4 cent and 7 cent stamps. So 4 cents is how far back we're going to have to go. We're going to assume K and back to 18, and then we're going to look at K plus 1. Well, I got to go 4 back, okay? Which means I got to have the first 4 of these things done, okay? All right, so let's look at the different ways of doing the first 4. Note that and let's see, 18 is 14 plus 4, right? Note that 2, 7-cent stamps and 1 4-cent stamp give us 18 cents postage. Also, and we need to look at 19 cents. 19 cents is what? So 12. So 1 7-cent and 3 4-cents, right? 7 and 12. Okay. Also, 1 7-cent stamp and 3 4-cent stamps give us 19 cents postage. Okay. And then also 20 is pretty easy. That's 5 4-cent. Give us 20 cents postage. And 3 7-cent stamps give us 21 cents. Thus, the initial step holds. Okay? So now we're going to look at, we'll let K be 21 cents, but then we're going to look at K plus 1 would be 22 and above. Well, for 22, we just go back to 18 and add a 4-cent stamp, right? For 23, we go back and add a 4-cent stamp to 19, right? And so on and so on. But that's why you have to do those 4 steps to start with. That's an expanded initial step. So we have to say this right. Now suppose, or now assume, suppose is kind of my proof by contradiction word. Now assume that we can get postage amounts 18 to K, and K has to be bigger than or equal to 21 cents. And let's consider K plus 1 cents postage. since we can get k plus 1 minus 4 cents postage. Now think about that. If that's 21, 20, 22, yeah, I'm sorry. 22 minus 4 is 18. So that's the first one, right? And then anything else above that we've got. Since we can get that postage, then get k plus 1 cents by adding a 4-cent stamp. Thus, the inductive step holds. And then the big finish, therefore, by strong induction, the statement holds. And you were done. Now that took a little while. We worked at that, but I was doing a lot of explaining, a lot of hand waving. Certainly didn't take that long to do the test. What I will do for you, I have added a 5-point curve to the test. That's me acknowledging that, okay, I didn't have the entire class ready to go on this test, so I'll give you a little bit back. What I will also do is, for any problem where you missed a point or more, I will let you get a point back on that problem if you will rework the problem. And since we weren't in class this morning, what I will do is I will try to contact you via email and let you know which problems you missed points on. The other thing that I'm going to ask is that if you made less than a C, you made below 70 on this exam, without the extra points and all that, I would like for you to come in and see me, and let's talk about these problems and where we go from here. I really want everyone to succeed in the class, but I think for a few of you that means you're going to have to bump it up a notch. And whatever it is you're doing now to prepare, it's not adequate. It's not enough. And if I can do something different to make that change, then I'll gladly do it. But I think really the burden here is going to be on the individual, because what it's showing me is that you probably have not worked a lot of the problems. You needed some help along the way to work some of the problems, and you didn't come to me to get it, or you didn't come to me enough to get it. You might have shown up a time or two, but not enough to make a difference. And that's what we've got to do. This is a tough course for people. It is a course where you're no longer just solving equations or working integrals or taking derivatives or whatever it is and just turning that crank. You really do have to think about, okay, how do I argue? How do I convince someone that this statement is true beyond a shadow of a doubt? And it's a different mindset. So it takes some practice to do this. Okay. All right. So I've already given you a lecture for stuff we would have worked on this morning. I'll probably by this evening sometime post another one just so we have more stuff to work on. But really, what I'd like you to kind of do is work on those problems. Anything that you missed at least a point on the test, I want you to rework that on separate paper and be ready to give that to me on Thursday. Okay, and I will give you a point back per problem on that. So part of it's my curve, part of it's you working a little extra hard to do it, and then I'll let you know if I want you to come in and see me. Okay? All right, that's it for today, and I will see you later.